Okay, somehow my link got broken. Maybe GeoGebra reorganized their pages or something, but I've re-uploaded this file, or a version of a slightly different version of this file. But you can explore this one on your own in GeoGebra if you want to. Okay. But moving along, kind of summarizing what that applet is showing us. So assuming that mu and sigma are the population mean and standard deviation, and n is the size of the simple random samples you're going to take, and suppose, in practice you may not know what mu and sigma are because they're coming from the population, but in theory, the mean of the sampling distribution of x bar, which we could denote as mu sub x bar, meaning if you were to average all of the x bars, it would actually be mu, which I know looks kind of weird there, but what it's saying is if you average all possible sample means, you can't go out and practice and take them all, but in theory, if you did and average them, you would get mu. So this is going to tell us how the population behaves, and it turns out in most cases it's a normal distribution, and we can use probability like we learned about the normal distribution. The standard deviation is going to wind up for x bar, winds up being sigma over square root of n, which is a good thing. It's actually less spread out than the original population. It gets divided by the square root of the sample size. Okay. So this is true, period, regardless of the sample size, regardless of the shape of the original population. Okay. It's always the case that your sampling distribution for x bar will have a mean of mu and a standard deviation of sigma over square root of n. Okay. Again, that's true regardless of the shape of the population and regardless of the sample size. If the population is normal, so it's normal with mu and sigma, then the sampling distribution will be exactly normal with mu and sigma over square root of n, regardless of the sample size. If the population is not normal, we need what's called the central limit theorem, which says as long as your sample size is large enough, x bar will still have an approximately normal distribution, as we saw with my GeoGebra applet. So this is what we call the central limit theorem. So when the sample size n is large, or if your original population is normal, if you don't have large sample size, the sampling distribution of the mean x bar, of the sample mean x bar, is approximately normal, and its mean is mu, and its standard deviation is sigma over square root of n. So that's the central limit theorem. If you take large enough sample sizes, x bar itself is approximately normal, with a mean of mu and a standard deviation of sigma over square root of n, where mu and sigma are the original population parameters for x. I have a link, which, of course, links die all the time, and if this one dies, you can just Google Rice sampling distribution applet, Rice University sampling distribution applet. This is pretty much the same thing as the one that I had, just showing it in a slightly different way. Let me see if I can find this one real quick. So the link in the applet did work, took me to this page. I clicked on a button and it opened up this applet. This one, you can change the original population. It started as normal, but you can make it as strange as you want it to be. And then you can calculate samples. These are of, you can do 5, 10, 10,000, 100,000. You can compute different samples. You can change the sample size. So you do different sample sizes. And you can even do, we're talking about the mean, you can do other statistics as well. We're mostly concerned about the mean right now. You can do fit normal, and it'll put a normal distribution curve through it to see what it's approximately fitting as well. So this thing shows me, I'll have to redo it here, that even if I have a population that's really weird shaped, if I take large enough sample sizes, and it usually doesn't have to be super large. They'll say in practice if it's at least 30, then you're probably going to be really safe. But you see here in the real simulation, if I do n equals 16 and I do it, it's already approximately normal when I do 10,000 or 100,000. And again, we're talking about all possible samples. So again, that's the central limit theorem. Regardless of the shape of the population, if you take large enough sample sizes, and you take all the sample means, in this case 10,000 or 100,000, and you plot those, you're going to get a normal distribution, or something that's approximately normal, and the mean will be the same as the mean of the original population, and the standard deviation will be sigma over square root of n. And in these notes, I just have one example of this. We'll do more examples in class, but here's an example. Based on service records from the past year, the time and hours that a technician requires to complete preventative maintenance on an air conditioner follows the distribution that is strongly skewed right, the one you see in the picture here. It's strongly skewed right, and whose most likely outcomes are close to 0, so they're usually going to complete the repairs very quickly, but it's skewed to the right. Some are going to take a lot longer. The mean time is mu equals 1 hour, and the standard deviation is sigma equals 1. So your company will serve us a simple random sample of 70 air conditioners. You have budgeted 1.1 hours per unit. Will this be enough? Okay. So my question is, the way I'm going to try to answer that, will this be enough, which is a pretty open-ended question, but what I'm going to do is use what we've learned here and look at, well, what's the probability that X bar, that the average repair time is going to be less than 1.1? Okay. So if we take simple random samples here and we look at the average, what's the chance that we're going to get an average less than 1.1? So that would be one way of figuring out if it's enough time. Are we on average going to be able to finish the repairs on time? So we can apply the central limit theorem because we have a simple random sample that's 70, pretty large. Okay. And again, how large you need is kind of it's not a well-defined thing. You know, once you start getting over 20, definitely over 30 is going to be big enough. 70 is very large, definitely going to be able to use the central limit theorem. And if you have a normal population to start with, it doesn't even matter if your sample size is large. But this one is not normal. It's strongly skewed right, so we need that large sample size of 70. But we've got it. Okay. So the central limit theorem tells me that if I take simple random samples, then the X bars that we get are going to follow a normal distribution with a mean that's the same as our population, which, based on the empirical data from the past, we have as 1 hour. And here's the big difference from chapter 3 to this chapter here, or the normal distribution chapter, whatever that is in your book, in a particular semester to this semester. Instead of just sigma, we have sigma over square root of n. Okay? If we're talking about X bar instead of X, the mean is mu, and the standard deviation is sigma over square root of n. So we have a normal distribution, and we know how to compute this probability. I can use normal CDF. Okay? We're doing less than, so if we shaded the picture, we'd be doing the area to the left. So we want to go from negative infinity up to 1.1. So we do normal CDF. Negative 1e99 was our way of doing a very large negative number to be as close as we can on our calculator to negative infinity. We have an upper bound of 1.1, a mean of 1, and sigma, I just let the calculator compute it here. I type it in like this, that my standard deviation is 1 divided by square root of n, so 1 divided by square root of 70, since it's sigma over square root of n, where sigma is 1 and n is 70. And you do that, you get approximately 0.8, okay? 0.80. So that means that 80% of the time we would expect, on average, to get less than 1.1 hours, okay? Is that enough? You know, that would kind of be your decision. I'm not sure I would be comfortable with that, to think that 20% of the time we might not finish in time based on this. You know, 80% of the time looks like it would be enough, 20% of the time not. So it's pretty high, but still, you know, what is that cutoff level? We'll talk more about that too as we go into future sections. You know, how high do you need these probabilities to be confident enough for what you're trying to say? But anyway, that's my example of how we can use the central limit theorem to solve an actual application here. We have, based on empirical data, we have a mean and a standard deviation for an original population, and if we take large enough sample sizes, we can assume that X bar would be approximately normal with mu and sigma over square root of n, and we can answer these types of probabilities using the normal CDF command on our calculator like we did in our chapter on the normal distribution.